Hello, everyone. My name is Fardin Bahreini. The title of this paper is Integrating Ontology and LLMs for Diagnosis and Repair of Concrete Surface Defects. We'll cover introduction, literature review, proposed framework, implementation, testing and results, and contribution and future work. Let's start with problem statement. The durability and safety of concrete structures depend on accurate and timely diagnosis of defects. Moreover, traditional diagnosis relies on manual inspection, which can be subjective and inconsistent. Also, while ontologies provide structured knowledge, their static nature can be a limitation in dynamic context-specific scenarios. And LLMs also can produce plausible but incorrect information and lack deep domain-specific grounding without guidance. The objectives of this paper are demonstrate how integrating ontology knowledge enhance LLM reasoning for concrete surface defects. Showcase the contribution of this synergy in improving response clarity and delivering actionable recommendation. Also bridge the gap between structured knowledge representation and adaptive AI reasoning. And validating the proposed frameworks through a detailed case study focusing on spalling defect. Let's move to literature review. Ontology-based query checks were used to reduce LLM hallucination in question answering. Moreover, integration of ontological reasoning into LLM workflows has also been explored for predictive maintenance in manufacturing. Similarly, combining ontological knowledge with LLMs proved effective for robotic tasks. The reviewed literature confirms that combining domain-specific ontologies with LLMs provide structured guidance and improve context-aware decisions. Moreover, ontologies act as a stable backbone, ensuring consistent semantic and preventing the generation of incorrect information. Existing studies emphasize guidance but do not focus on using a specific ontology-defined thresholds to enable flexible adaptive reasoning. We distinctively employ OCSD's predefined threshold to tailor LLM reasoning for a specific structural defect diagnosis and repair scenarios. Let's move to proposed framework. The proposed framework integrates ontology-driven reasoning and GPT-4o defect analysis modules. OCSD provides semantic relationships and severity thresholds for classification. GPT-4o fill gaps, the knowledge gaps using pre-trained knowledge capabilities informed by OCSD variables, and iterative reasoning enable dynamic updates from new inspection data or feedback. The proposed framework has two main modules. The first module is ontology-driven reasoning module, which leverage the OCSD to map defect attributes to semantic relationships for classification, causal analysis, and severity assessment. The second module, which is defect analysis and recommendation module, integrates semantic attributes and ontology reasoning with GPT-4o to generate actionable insights and repair strategies using the 3R repair, rehabilitation, replacement processes. The system uses dynamically inserted variables from the ontology to create context-aware prompts for the LLM at runtimes. Interactive visualization of the ontology relationships are used to make the reasoning process transparent and intuitive for the user. Let's move to the implementation. A prototype system was developed using Python libraries for ontology parsing and querying. The prototype generates interactive graphs of relationships. Moreover, OpenAI API integration enables dynamic GPT-4o prompt execution. The system supports automated data ingestion, dynamic ontology querying, and interaction with the LLM in a reproducible environment. This figure shows the user interface of the prototype system. As you can see in different parts, like A, the user can upload the image of the defective area. In the B, they can get the defect attribute based on the LLM reasoning, and then also if there is any specific information the user wants to provide, they can put it here. Also, the interactive visualization shows all the ontology information related to the specific type of the defect, and then they can analyze and they can get the causal and remedial action for the defects. This figure shows an example of interactive visualization of OCSD-derived thresholds for condition assessment of spalling. For example, for light spalling based on Ontario Inspection Manual, the depth value is less than 25 millimeter, and the width value is less than 150 millimeter value. Let's move to testing and results. We compared a baseline model GPT-4o only with our OCSD enhanced model. So we have a detailed comparison in our paper, but for some example, I have here example of defect 1. The baseline model suggested low severity, whereas the enhanced model using OCSD thresholds correctly identified it as a medium spalling. For defect 4, the enhanced model provided a more precise severe spalling classification and recommended a standard-based repair actions unlike the baselines generic advice. Also, the results demonstrate that grounding the LLM with the OCSD leads to more contextually accurate and actionable guidance. Let's move to evaluation metrics. The evaluation focused on 4 key metrics: severity classification, cause identification, repair actions, and preventative measures. The terminology for evaluation was drawn from the recognized industry standards, including the Ontario Structure Inspection Manual, and the OCSD enhanced model demonstrated a significantly higher frequency of correctly identified terms across all metrics. This figure shows the frequency of correctly identified terms across the 4 defined metrics. Also, a radar plot visualization confirms the enhanced model's more comprehensive and balanced performance compared to the baseline. Let's move to conclusions and future work. OCSD and GPT-4o integration grounds LLM output in a structured domain knowledge. Moreover, adaptive reasoning framework boosts accuracy and transparency in diagnosis. The prototype provides a reproducible environment for inspection and repair workflows. Also, the evaluation confirms significant enhancement in actionable repair recommendations. Let's move to limitations and future work. The current OCSD may not cover all possible defect types, causes, and repair strategies. The quality of the LLM's output is highly dependent on the clarity and specificity of the input data. Moreover, reliance on a commercial API for GPT-4o introduces computational costs that could be a challenge for larger scale deployment. The future work will focus on expand the OCSD by incorporating additional classes and relationships to improve the coverage of the ontology, and fine-tune domain-specific LLMs and integrate advanced 3D semantic segmentation to enhance the precision, and also explore strategies to optimize computational costs for a more sustainable and scalable implementation. Thank you for your time.